It's been a minute, as the kids say, since we had an episode of The Scientist. And that's because I've been incredibly busy doing science myself, traveling around the world, attending conferences, speaking at conferences, and doing podcasts galore, as well as teaching, research, travel, family stuff. And so apologize for the long interregnum, but some of it was used for generating material that we will be encountering today in this conversation, which I'm going to call the Pope of Physics. That's right. It's about Enrico Fermi, one of the last great universal scientists, and one of the most fitting people to have featured on this podcast. Today's conversation with myself will be largely based on two books. One is called The Pope of Physics by Gino Segre and Bettina Harlan. And the second one was by David Schwartz, and it's called The Last Man Who Knew Everything. Still hoping to have David on the podcast. He's written so many great books, and this is one that you don't want to miss as well. So let's begin. We're at Trinity Site, New Mexico, 5:29 a.m., July 16th, 1945. The first atomic bomb detonated with the force of 20,000 tons of TNT. Everyone hits the ground. Everyone except for one man. Enrico Fermi stands outside the bunker, 45 years old, already a legend. He's not looking at the fireball. He's not contemplating the philosophical implications of splitting the atom. No, he's holding up a torn piece of paper. The moment the shockwave, that wall of compressed air racing across the desert at the speed of sound, hits them, Fermi drops these scraps from shoulder height. They flutter in the blast. He walks a few paces, measures the displacement, and pulls out a slide rule. 2 minutes later, he announces 10 kilotons. The actual yield, 22 kilotons, but not bad. In Gino Segre and Bettina Harlan's magnificent biography, The Pope of Physics, they write that the dropping of the paper pieces soon became yet another vintage Fermi story, adding to the lore of how he could, with the simplest of means, estimate the magnitude of almost any physical phenomenon. And then comes the final line, the line that defines him. His colleagues in Rome used to joke, Fermi was infallible, just like the Pope. That is Enrico Fermi. While others would philosophize about fire stolen from the gods and Prometheus's fall from grace, Fermi measured it. They called him the Pope not because he was literally infallible, but because whenever Fermi spoke, the argument was effectively over. He was born in 1901 in Rome. He died prematurely at age 53 in Chicago, a Nobel laureate. In between, he invented the nuclear age, discovered the weak nuclear force, calculate what happens when stars collapse, teaches a generation of Nobel Prize winners himself, and revolutionizes physics forever. He does physics in the morning, theoretical flavor of physics, experimental physics in the afternoon after a cappuccino, perhaps. He builds his own furniture at night. Badly, it turns out, but it did work. This is a story of a man who believed that everything worth knowing could be known, and then he proved it. If Einstein is the poet of physics, Fermi is the engineer. Einstein asks why. Fermi asks how much. And in a world drowning in complexity, mysticism, and hand-waving, Fermi's clarity is the weapon we need most. 1914 in Rome. Il piccolo fiammifero, the little match. Picture Rome before World War I, a city of ancient stones and new electric trams. Horse-drawn carriages give way to automobiles. The Fermi family lives in Via Gaeta, middle class but rising. Alberto Fermi, his father, works for the Ministry of Railways, disciplined, orderly, ambitious. Ida de Gattis, his mother, is a schoolteacher, intelligent, demanding, emotionally distant, it's told. They have 3 children, Maria, Giulio, and Enrico. Giulio and Enrico are inseparable. 17 months apart, they might as well be twins. They build everything together. Electric motors from scrap wire, gyroscopes, miniature steam engines. When the family walks through Campo de Fiori, the boys lag behind, debating whether a certain kind of top will precess counterclockwise or clockwise. Enrico is actually the quiet one, and Giulio is the spark. Then, January 12, 1915. Giulio is supposed to undergo a minor throat surgery. Routine, they said. A swollen gland, nothing serious. But the anesthesia goes wrong. He never wakes up. 14 years old. Alberto Fermi sobs in the street, first time anyone has ever seen him cry. Ida collapses into a depression that never lifts. And Enrico, the silent shadow brother, he goes silent. For weeks he says almost nothing. But here's where Segre and Harlan reveal in The Pope of Physics. Before Giulio's death, when little Enrico first returned from the countryside at age 2.5, his sister remembered him as a small, dark, and frail-looking boy. When he saw his family for the first time, strangers to him after years away, he began crying. His mother told him to stop at once in the home. The naughty boys are not to be tolerated. Little Enrico stopped crying, but the emotions didn't disappear. In The Pope of Physics, we learn that with bottled-up frustrations, he was known to occasionally break into flaming rages, earning him the nickname of Piccolo Flammifero, the Little Match. The Little Match, the boy who could ignite and would ignite the nuclear flame for the first time. That nickname would follow him his entire life. Even decades later, Fermi's rare but volcanic eruptions would be obvious when he was pushed too far. Grief could become rigor. Pain could become his precision. He can't bring his beloved brother Giulio back, but he can understand why things fail, while hearts stop, while anesthesia lacks what the universe obeys, laws instead of prayers. Every scientist, every great founder, everyone who does anything great has that moment, the wound that becomes fuel. Steve Jobs, abandonment. Elon Musk, brutal South African childhood. Richard Feynman, his wife Arlene's death from tuberculosis. For Fermi, it happened early on, his brother Giulio. He channels his loss into logic, because logic, unlike people, doesn't lie. At age 13, he starts haunting the Campo de Fiori market. There's a bookseller there, used scientific text, old journals. He buys a 2-volume Latin treatise, Elementary Physics of Mathematics, by Andrea Carafa, written in 1840, 900 pages. Dense, obsolete, even then. But Enrico doesn't care about modern. He cares about complete, about the fundamentals, about the foundations. He devours it, rederives every proof, finds an error in one theorem, and writes a correction in the margin. He's teaching himself university-level mathematics at 13 years old because no one else can keep up with him. Then he meets Adolfo Amadei. Amadei is a colleague of Fermi's father, an engineer, a self-taught polymath, the kind of guy who reads Poincaré for fun. One day at a family gathering, young Enrico approaches him. Is it true there's a geometry that doesn't use measurement? Most adults would pat the kid on the head. Amadei recognizes predatory curiosity. He lends Enrico a copy of Geometry Projectiva, The Projective Geometry by Ray, a dense graduate-level text on projective geometry. And he devours it. Every problem was solved, every theorem rederived from first principles. Amadei later writes, I realized I was in the presence not of a student, but of an instrument of nature. That's the thing about outliers like Fermi. You don't teach them, you aim them. Before he becomes the Pope, he builds his mental architecture, his mental Vatican. Most people learn to solve problems by following recipes. Fermi invents approximation as an art form. You've probably heard of Fermi problems, the Fermi paradox. Like, how many piano tuners live in Chicago? How many atoms are on the sun? How many blades of grass can fit on a soccer field? They aren't party tricks. They're a way of building your cognitive infrastructure, and we physicists use it all the time. Here's how we use it. We break the impossible into something that's estimatable. You don't know how many piano tuners there are in Chicago, but you can estimate Chicago's population, about 3 million. The average household size, about 3 people, 1 million households, therefore. How many households have pianos? Maybe 1 in 20, so 50,000 pianos. How many pianos tune per year? Once per 50,000 tunings per year, but tunings per tuner may be 1,000. That results in 50 tuners. And the actual number was estimated around this time to be about 83. Close enough to act, close enough to learn. Fermi's philosophy was never make a calculation more accurate than was necessary. It's not laziness, it's efficiency that you can harness. Over-optimization kills momentum. Perfection is the enemy of the good enough. Startups die from perfectionism, not from prototypes. Fermi understood better to be approximately right and moving than precisely right and stuck. This becomes the foundation of modern engineering. McKinsey's case study interviews, Google exams to get a job at Google, and back of the envelope startup culture that we have all heard about and seen in movies. If you've ever written quick sensitivity analysis suggests, or order of magnitude we're looking at, you're thinking like Fermi. That's his cognitive operating system, installed in every technical mind since 1930, and we physicists crave it and love it. 1926, the quantum revolution. Fermi is 25 years old. Italy creates its first chair of theoretical physics specifically for him. He moves to Rome, into a decaying villa on Via Panisperma, number 89A. The building has palm trees and bamboo thickets in its garden. A high wall shields it from the dusty street. Fermi does what builders do. He assembles a team of misfits and renegades. Amaldi, the experimentalist, who is steady and unflappable. Emilio Segre, brilliant, abrasive, but with restless energy, also the co-author of The Pope of Physics. Yes, his own student would later write his own biography 60 years later. Bruno Pontecorvo, charming, radical, but eventually a man who defected to the Soviet Union, helping them with their atomic ambitions. Franco Rossetti, a naturalist, a mountaineer, he refused as a pacifist to work on nuclear weapons. And one of the most tortured geniuses of all time, arguably more talented Fermi himself, Ettore Majorana. He disappears mysteriously in 1938. I'll have a conversation with João Magajo, who wrote the book about Majorana in the coming year. They call themselves the Boys of Via Panisperma, Il Ragazzi. It's the park of Europe, the Bell Labs of physics, built in a crumbling villa with spare wire and sheer will, and no Wi-Fi. Fermi leads not through charisma. He's not that charismatic. He learns through competence, so overwhelming, it becomes a gravitational force that's irresistible. His rule is every theory must produce a measurable prediction within 6 months, or it's philosophy, not physics. No mysticism, no hand-waving, no interpretations that can't be tested. That's why they worship him. Other physicists, Heisenberg, Dirac, Bohr, they would speak in riddles, in Copenhagen interpretations, and complementary principles that Fermi disdained. Fermi spoke in numbers you can check. He does something that almost no one else can. Theory in the morning, experiment in the afternoon. He doesn't just predict what the universe should do, he builds the machines that prove it. And here's a detail from the Pope of Physics that captures the group's culture. Every late afternoon was sacred. The boys would gather. Fermi would lead an informal discourse, sometimes on a topic he chose, sometimes on whatever was perplexing the group. Without consulting any text, Fermi would derive all the relevant formulae from memory, solve the problem in real time, consider follow-up questions, do it all so smoothly students didn't realize it was improvised, all without ChatGPT to help him. This wasn't lecturing. This was intellectual jazz, the jazz of physics, as my friend Stefan Alexander says. One student said, when Fermi calculated, the universe obeyed. Okay, you'd be forgiven for thinking that he might be suffering from a little bit of hero worship and lionization, but wait, there's more. It's technical from here on, but stay with me because this is foundational. December 1933. Pauli has proposed something desperate, the neutrino, a particle with no charge, possibly no mass, and something that would be nearly undetectable. It's a Hail Mary to save the law of conservation of energy and beta decay. See, it was known that radioactive atoms sometimes spit out electrons, but this energy doesn't add up. Something is missing. Pauli invented the neutrino to patch up the books to make them balance. Fermi looked at the books and says, I can make this quantitative. In 2 months, he writes the theory of beta decay, what we now call the weak nuclear force. This is one of the 4 fundamental forces of nature: gravity, electromagnetism, the strong force, the weak force. He invented the mathematical structure for the latter. He derived it from Firth's principles. Quantum field theory applied to the nucleus, something I just finished teaching to my quantum mechanics 2 students at UCSD. He calculated the decay rates, the energy distributions, interaction probabilities, and this was only soon after he'd invented the technique that we call Fermi's golden rule, which explains how two-level systems like lasers can be described quantitatively in terms of density of states and energy eigenvalues. It's an incredible tour de force, and then he immediately applied a theory to an experiment in order to predict the outcome that would be observed. So yes, this is where the golden rule comes from, that you learned about in quantum mechanics, the transition rules. That comes from Fermi himself. And for the hardcore quantum mechanics nerds, my Physics 130B brilliant students that just finished up their term with an average grade of about A minus. This is called the Fermi contact term. It's crucial for understanding the hyperfine structure of hydrogen, which is the most abundant atom in the known universe, and it's the most abundant transition between a two-level state system that can arise. So we got a tremendous deal of information about quantum mechanics that was predictable. And in fact, it's one of the most exact and measurable lines in the known universe. Fermi understood this, and radio astronomy owes maybe some of its existence to this side hustle that Fermi had developed along the way to developing the theory of the weak nuclear force. However, this paper that he submitted to the journal Nature rejected it. Too speculative, they said. He published in an obscure Italian journal instead. 5 years later, it was recognized as one of the most influential papers of the 20th century. Even genius gets rejection letters. Even nature can miss paradigm shifts. Fermi doesn't sulk, he moves on. Because Fermi doesn't build his identity on validation. He builds it on output. James Chadwick discovers the neutron in 1932. By 1934, Fermi's team is bombarding everything in the periodic table with neutrons just to see what happens. They hit uranium, element 92, the heaviest natural element known. The results are bizarre. They're creating radioactive isotopes they can't identify. Fermi thinks maybe we've created something new, element 93, a transuranic element. He publishes it. He's wrong. It won't be the first time, wasn't the last time. What he's actually done is he split the atom. He discovered nuclear fission, and he didn't initially realize it because he was looking for something else, confirmation bias. By the way, this is sort of the essence of serendipity in disciplined experiments. I talk about this in my first book, Losing the Nobel Prize. You find what you're not looking for, but only if you're not looking hard enough. And this is because it's one of the most pure examples of scientific practice, and that's because you don't expect it. So you're not relegated to the dispositions of confirmation bias. So I claim that serendipity is one of the most pure things that a scientist can invoke, except the problem is, as I say, quoting my hero Yogi Berra, actually I made this up, but I think Yogi Berra would like it, serendipity is awful hard to plan on. 4 years later, Lisa Meitner and Otto Hahn figure out what Fermi actually did. But here's the experimental innovation that matters. Fermi discovers that if you slow down neutrons by passing them through paraffin wax or water, moderating them, they're 100 times more effective at inducing reactions. That's weird. Wouldn't it be better to have faster zipping around neutrons? No, they zip right past them when they're too fast, but slow neutrons linger. That gives more time to interact, higher probability of capture. This is the key to every nuclear reactor ever built. It's also why he would eventually win the 1938 Nobel Prize for the, quote, demonstration of the existence of new radioactive elements produced by neutron irradiation, and for his related discovery of nuclear reactions brought about by slow neutrons.
This year's Nobel Party became a brilliant event. The whole of representative Sweden had Saturday, the 10th of December, taken their seats in the concert hall. When the royals took their places and drew straps to the Fagnen, when everyone so happily took their seats and played, the Concert Association's orchestra, the Nobel Foundation as chairman, County Chief Hammarskjölds gave the greeting speech. Then the prize and Meister singers played it with so Professor played. Lucky that he arranged this year's Nobel Prize winner Enrico Fermi as unhelpful. Barely then got up, and shy and predictable got up for the table to receive the diploma from the king's hand, and the check the king shook. Hearty hand with Professor Fermi, surfaced a few kind words, and the whole audience applauded.
Fermi doesn't just stumble onto fission. He invents the technique that makes nuclear engineering and eventually weapons possible. That's the difference between discovery and invention. Discovery is sometimes accidental, serendipitous, but invention is method and practice. 1938, November. Fermi wins the Nobel Prize in Physics. The timing is not accidental. Mussolini has just signed the racial laws, Italy's version of the Nuremberg laws. Fermi's wife, Laura Capone, is Jewish. If they stay in Italy, they'll die. The Nobel Prize ceremony is in Stockholm. Fermi knows this is his golden ticket out. They pack lightly. A few clothes, some notebooks, nothing that screams, we're fleeing this fascist country. December 10th, Alfred Nobel's death date, and the day that the Nobel Prize gets accepted from King Gustav V of Sweden. The 24th, on Christmas Eve, Fermi family boards the SS Franconia in Southampton, bound for New York City. They never returned to Italy. Imagine, you're 37 years old, you've built the greatest physics lab in Europe, your students are your family, your language, your culture, your entire intellectual infrastructure is gone like that. But your wife lives. Your children live. That's the trade. Fermi makes it without hesitation. This is his integrity. This is his knowing the cost of his values and paying it anyways. 1939 January, Fermi arrives in New York City with $50 in his pocket and a mind full of neutrons. He joins Columbia University. Within weeks, Leo Szilard burst into his office, wide-eyed, Hungarian, prophetic. Fermi, listen, if we bombard uranium with neutrons and it splits, it releases more neutrons. Those then hit more uranium atoms. Chain reaction. Do you understand what this means? Fermi understands. It was partially part of the reason that he understood how the Fermi Golden Rule could be applied to the laser problem of stimulated emission, which is quite unusual and unexpected. And we'll talk about that when we talk more about Einstein and Fermi in the future. It means you can release the energy that holds the matter together. It means you can boil a city. But first, you have to prove it's possible. December 2nd, 1942, underneath Stagfield, University of Chicago. Under the west stands of an abandoned football stadium, Fermi and his team build CP-1, Chicago Pile Number 1. The war is on. It's not a reactor in any modern sense. It's a pile, literally. 400 tons of graphite blocks, 50 tons of uranium oxide, 6 tons of uranium metal, stacked like Legos by human hands. No blueprints, no safety containment, no simulation software, no HR or OSHA on hand, just Fermi's calculations on a blackboard. The design principle, graphite slows neutrons. Uranium absorbs slow neutrons and fissions. Each fission releases 2 to 3 neutrons. If the multiplication factor K is greater than 1, the reaction is self-sustaining, a chain reaction. Simple, except if K gets too high, you might melt Chicago like a deep dish pizza. So, Fermi installs control rods, cadmium strips that absorb neutrons, stuck into the pile like toothpicks keeping up a canopy. December 2nd, 3:25 p.m., he orders, pull the final rod halfway out. The neutron counters start clicking, faster and faster. Arthur Compton watches the graph paper, exponential graph curve climbing. Fermi watches his slide rule. 3:53, Fermi says quietly, the reaction is self-sustaining. That sentence ends one era, the pre-nuclear era, and begins another. Before that moment, humans could burn things like wood, coal, oil, chemical energy, electron rearrangements. After that moment in December, humans can tap nuclear binding energy, the force that holds matter itself together. It's the difference between a firecracker and a literal nuclear bomb. Eugene Wigner pulls out a bottle of Chianti, smuggled in for this moment. They pass it around and drink out of paper cups, but nobody speaks. What do you say when you've just unlocked Prometheus's fire? Fermi goes home, tells his wife Laura, the Italian navigator has landed in the New World. It's a code. She gets it. Fast forward, 1943, Los Alamos. Fermi is recruited to Los Alamos, the secret city in New Mexico, where they're building the bomb. Oppenheimer's the director, the philosopher king, quoting the Bhagavad Gita, chain-smoking, holding court. But Fermi is the plumber. But he's a brilliant plumber. Oppenheimer worries about the soul of science. Fermi solves the differential equations themselves. There's a problem with implosion, call Fermi. Neutron transport, tamper material is too high, call Fermi. The initiator isn't triggering fast enough, Fermi. He becomes the go-to guy for impossible calculations. Richard Feynman, who we met earlier in this series, himself a calculation machine, later writes, Fermi had a way of reducing any problem to its essential elements so that the answer was almost obvious. That's not simplification, that's clarity under pressure. And here's where Fermi's moral architecture shows up. After the war, the US government wanted to build the hydrogen bomb. Fusion, not fission, 1,000 times more powerful. Edward Teller is obsessed with it, calls it the super bomb. The Atomic Energy Commission asked Fermi to join the General Advisory Committee to evaluate whether they should build it. October 49, Fermi and Isidore Rabi write a minority report. It is necessarily an evil thing considered in any light. The fact that no limits exist to the destructiveness of this weapon makes its very existence and the knowledge of its construction a danger to humanity as a whole. They recommend against it. Truman ignores them. The H-bomb gets built anyway. And here, the pulp of physics reveals something telling. Years later, when a colleague confronted Fermi about working on devastating weaponry, Fermi flared up. The little match ignited. They left shaking and speechless. She witnessed Fermi's occasional outburst before, but had never borne the brunt of the temper himself. That wound would never heal. But here's the point. Fermi doesn't walk away from science just because science gets weaponized. He stays in the room because, like Alexander Hamilton, you need to be the room where it happens or someone else will take your rightful seat. That's complex integrity, not purity, moral or otherwise, but engagement, even knowing the consequences.
I feel impelled to speak today in a language that, in a sense, is new. One which I, who have spent so much of my life in the military profession, would have preferred never to use. That new language is the language of atomic warfare. The atomic age has moved forward at such a pace that every citizen of the world should have some comprehension, at least in comparative terms, of the extent of this development, of the utmost significance to every one of us. Clearly, if the peoples of the world are to conduct an intelligent search for peace, they must be armed with the significant facts of today's existence.
And this has been part 1 of Enrico Fermi. We need to do a part 2. We need to cover the Fermi paradox. We need to cover his final years. We need to discover the connections between humanity and the stars. Because Fermi asks out of nowhere to my late great colleague, Herbert York, where is everybody? And thankfully, Fermi is there to estimate. Thanks for joining us on this part 1 episode of The Scientist. We'll have part 2 very soon, featuring Enrico Fermi again, and these wonderful books by Schwartz and Segre and others. And we'll have some resources and some B-roll footage and maybe some fun simulations as well. So I hope you've enjoyed it. Please be sure to subscribe to both channels. The Scientist has its own podcast channel, and of course, Into the Impossible, we broadcast it too. Trying to grow both podcasts. They serve sort of different purposes, and they're at the mercy of different algorithms. So I hope you'll join us on this wonderful series that I'm getting so much enjoyment out of, The Scientist. Thank you so much. See you next time.